Hello. So today we will continue on the Braid group action on Milnor Fibration. So let's recall what we did last time. So first of all, we define model then twist on the cotangent bundle of Sn, which we identify as the tangent bundle of Sn. So what I draw is just TS1. Okay, and then what the then twist did is to uh, turn around the zero section. So zero section, let me call it Sn. So okay, and remember we introduced the cutoff function. So I think I find in another paper of Seidel called the graded Lagrangian manifold, which is one of the reference today. He used the simpler cutoff function. I think is what Brian mentioned last time. So you just use pi and then go down maybe to 2 over 3 times over 3. Okay, so it's not like the symmetry cutoff function. Brand, this is what you talked about last time, right?
Yes,
Okay,
yes.
easy one. Yeah, okay. And then so after we have this model 10 twist, then we want to generalize it on a general Lagrangian n sphere. So to get this, you need to embed your sphere as an Sn. So we use the language called frame Lagrangian sphere. So of course you need to find some tangent space, tangent bundle like neighborhood around this Lagrangian sphere. So you find one embedding of your cotangent bundle into your symplectic manifold. Okay, I think this one is not very important, but let's say we fix it as one. So and then the Sn part of it should be your Lagrangian sphere. Okay, and you should think of your there's an embedding, there's a frame Lagrangian sphere, because you need the Sn to help you to do the then twist. So you should also have this embedding here. Okay, and then do the usual thing. So you first take your Lagrangian sphere. Sorry. Take your Lagrangian sphere and then go back to Sn and then do the then twist and then put it back. Okay, and then so since this has to be a symplectic automorphism, you need to extend it all around the place. So all around the place is you extend trivially over your symplectic manifold. Okay, and then we get a symplectic automorphism of M. So you can see that I put a L here. So it's like this embedding is recorded in this then twist. But we will discuss later that actually this embedding is not very important. Okay. Any question? Okay. Um, Next, we also discuss one thing is so monodromy in the symplectic manifold is equal to the dentist. So what does this mean? So let's say the end path of your path, let's call C, is the singularity, and then you're starting from arbitrary path, arbitrary point in your manifold, and then if you do one monodromy around this singularity, this monodromy is actually the same as the dentist on the Lagrangian sphere VC, where VC is this the boundary of this call it Lifshitz timber last time, is it? So from this path you can get all the vanishing cycle, become a point at a singularity point, and then join them together, and then take the boundary of this so this is the VC, okay, and this is in the pi 0 of symplectic of let's call it ECA. Okay, so you go from CA, the fiber of CA, and then come back to exurf. Okay, this is what we taught 2 weeks ago. Okay, in the paper of a long exact sequence of can't remember, the Seidel's paper. Okay, any questions? No. Nope. So now today we go into the AN configuration sphere. So let's draw one picture here. So let's say we take A4, say A4. So the picture you have is like something like this. And then you got 4 punctured point. 5, sorry, it's 5. And then so we look at this kind of path connecting these puncture. Okay, and then I think we discussed how we get a Lagrangian sphere out of this. So at the point you get a single point, the zero section, and then it gets larger and then getting smaller when you reach another puncture or the singularity point. So if you join them together, it's a Lagrangian sphere. Okay, so this is a Lagrangian sphere. So maybe I can remind you how we get this. So above this this is a fiber. So what is this fiber? The fiber is just the zeros of the polynomial intersect with the ball. So which polynomial we are looking at? We are looking at the AN singularity polynomial, and then we do some deformation so that it is a Morse function. So that the singularity point is non-degenerate.
Is that
Yep.
M or an N? So the EW equals to the first line is 2N plus 2.
2N
The
plus
second line
plus.
becomes 2M.
Oh, sorry. Should be 2N. Should be the same. Yep. So N. Okay. So N is governing the. Okay. So let me write down. N is governing the cotangent bundle you're using, and then M is governing how many puncture. Okay, and also which Braid group you're using. So yeah. And then okay, and oh, actually, there's a theorem. There's a lemma, and I have something to ask Brian from this lemma. So this lemma is LWC. So we already formed this sphere, right? So we need to prove that it is actually a Lagrangian submanifold. So they Coral Seidel done it in their paper. So a lot of argument they use exactness. Maybe the flow cohomogenic exactness to compute will be compute easier if it is a exact submanifold. So can I ask Brian what does this what is this cohomology mean?
What is
I
so
know
LWC is that
is the
Lagrangian
right.
sphere in the total space. This
Uh-huh.
and then the Lagrangian, you have a boundary. So this is for any submanifold. But sometimes we boundary could be empty, right? But if you have a boundary, but that what is but theta is okay. So this is theta is a symplectic one form. Only d theta is a symplectic form.
Yeah.
So that is just by definition, right? Is so that means theta w restrict to L is d of some functions.
What is the difference between this and this without the boundary?
But if the no boundary, is the same. Right?
Oh,
If there is a boundary, then let's say that the boundary is fixed. So the
okay.
like a function zero essentially is function the
How can the
fixed boundary.
homology change like after you fix the boundary?
But if Poynting dual, if you have many with boundary, the Poynting dual, one is with boundary, the other without boundary. So this is a first homology group without boundary. But I think in the examples, there's no boundary. Right? There is boundary? Where is boundary? LWC. Is that a boundary here? LWC.
Is this the boundary?
This Lagrangian sphere. It's Lagrangian sphere. When the sphere, there's no boundary for sphere. It's not. I mean, that when you draw that, there is not the boundary. That it is the you have vanishing cycles. You see the sphere, and then you get smaller. That is a disk, like a ball. When you have two balls, then it's again in the sphere. There's no boundary. I don't see where is the boundary.
No boundary. Like let's say if for smaller n, then
if there is the boundary, and then let's say that
like if your Lagrangian sphere is a S1, do you have the boundary? Do you have boundary?
No, that was the sphere. There's no boundary for any spheres.
No.
And with disk, you have boundary. So why do they use? I mean, certainly there's no boundary. I mean, there's no boundary for Lagrangian sphere. So it is a sphere.
Oh.
Maybe he said, maybe I check. So he said that for this is not for sphere, maybe general. Okay.
I think this is for.
Okay. This is LWC, so that is no boundary. I don't see where is the boundary.
No boundary. Oh, okay.
It means it's a sphere. There's no boundary for spheres.
Okay. Okay.
And probably we can just ignore that.
Okay. Okay.
Exact. When we say exact Lagrangian means this one form, which is in the sympact form is d theta. So sympact form restrict to L is 0. So we know that d theta is 0. So theta w restrict to L is closed. And restrict to L means exact. There, I don't think there is any boundary. This is.
Oh, okay.
I mean, this is exact Lagrangian sphere. LWC is a sphere, so there's no point to have a boundary. I don't see why there is a boundary here.
Okay.
So this is lemma 6.12. Check.
Okay.
You can continue when we.
Okay. Okay. So yep. So we continue the discussion just now. So now. Okay, now. So this is from remark 5.1. Yep.
Yeah, I've got a question.
Yep.
So the LWC we've talked about using the coefficient R, right?
Coefficient R.
Then that's topologically a sphere, but in the two singular point, the 2 points, the point, is that smooth? So we can talk about R coefficient.
Is comb over in that smooth? But it's a cone over a sphere. So it's like it become a ball.
Okay.
Right, smooth. Yeah, maybe not smooth. It should be smooth, otherwise only. You say Lagrange submanifold, so it has to be smooth.
Okay.
Oh.
I guess that's a low boundary. That's just like a typo. There's no need to have boundary.
Oh, because I think it's because the previous section is general Lagrangian submanifold, so they continue the use of the term.
The boundary is empty. Because it says Lagrangian submanifold. If you look at that, it's diffeomorphic to the n sphere. So it is a sphere.
Yeah, I think the smooth part they use some smooth square root thing, which I don't completely understand. You can go look for this paper here.
It is, the path is smooth embedding path. Okay, they have a model. They can write it out. So Yeah, there is a way actually in the local model. This is in this local model. They have explicit expression, I mean, like parameterization, and they just smooth. They choose a square root. Yeah, you have to choose this path. I mean, parameterize. It has choose. Yeah, there is a way to get a smooth. It is. Essentially, you have a sphere which is getting smaller and smaller. You only need to control the speed of this shrinking. It's not if everything is smooth.
Oh, so that function, so the function is controlling
you choose the path, right? The path, you can choose the path. I mean, I choose the parameterization of this interval. It's 1 to 0. You choose the speed.
Oh, okay.
So it's, I mean, if we choose a speed function from interval, like you can make it smooth. So it's like a no certain term, right?
Okay. 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 So, yeah. So we continue. Okay. So okay, from this Seidel paper here, so he say that actually it is open that whether the den twist is depend only on your Lagrangian sphere. Okay, but what can they show is if the two embedding has the same image of sphere, then this combination is isotopic to identity in the diffeomorphism of Sn.
I've just got on.
What?
I've just got Kovanov Seidel paper up lemma 612, as you're saying. I'm trying to work out, maybe shine some light on your question about the relative cohomology. They actually define LWC for C of path as a disjoint union of points X in the path of the sigmas. Now, I just wondered whether the path includes the two endpoints. I've forgotten what, strictly speaking. There's.
Oh, sorry. Yeah. So, oh yeah, right. So for this particular lemma, this C, if C have to have two endpoint in the singularity point. Yeah, the punctures.
So they're not in the actual path, is that right?
What do you mean by actual path? Connecting the boundary of the disk?
The disjoint union of the sigma over each point of the path.
Yep.
Are the endpoints in that disjoint union or excluded? I mean, are you missing the north and south poles of the sphere, or do you have them in there?
You said it's diffeomorphic to sphere. If you remove two poles, then you're not.
Yeah, I mean, if
sphere.
you need the two endpoints to be there to be a sphere. Otherwise, it's a punctured sphere. So it does have a boundary. So it could have a boundary if the two endpoints aren't included.
But
it has to be sphere. If you remove two, then it's not quite a sphere.
Yeah, it's punctured. It's a once or twice, depending whether you eliminate. But I just don't know what the definition of the path C is exactly, whether it includes the endpoints or not.
Usually it's included.
You should include.
Yeah.
I mean,
It's included, I think.
Yeah, C is always. So section 3A should be C. Even in the path, usually you can't have open path of. C is a path, is a curve joining 2 points, so it has to be.
Yep.
I think this relative homology, that's not really, probably that's just typo. I think it's not
very important.
Very important. Sometimes you may have why you have a boundary. When you see a general statement, you may have a boundary, but
okay. Yeah, so if you have two embedding with same image, and if you take one inverse and then compose with each other, you get the identity in the diffeomorphism of Sn. Then you can actually prove that the both den twist is the same. Or
so the isotopic, you mean in the connect components, right? So it in the same, so L prime in the same connect components.
So the L prime are from Sn to L.
Oh, I see. Okay, so it's a composition L prime and L inverse. So it is isotopic, right? It's not iso. It's
isotopic.
isotopic.
Yep. Isotopic. Yeah, isotopic. Sorry. Isotopic.
So it's joined to the identity. So
it's, Or they just differ by an rotation. Is you also can prove it. So then yeah. So actually they can show it for n less than 3, such that the den twist is only depend on L, because the pi 0 of df Sn is 1. But for higher n, this may not be non-zero. So for higher n, pi 0 of df often. Okay, so we come back to these the property that hold by these den twists. Oh, actually I want to ask Brian as well. So does this mean that so for the den twist just now, let me draw it again. So for the den twist just now, so I can twist it this way or this way. There should be the same den twist, is it? So this is
what do you mean? That's the
because I need to choose the orientation of the sphere first and then do the antipodal.
Antipodal map. The antipodal map, I think you need orientation, preserve orientation. So usually, So this is oriented. And then the floor, which is like different and preserve orientation. So usually there's only one thing. You have to preserve orientation.
Preserve So if I choose a sphere this way, and then choose the orientation this way, and then choose the other orientation this way, but this two should have this kind of property, is it? Like that.
Okay, sure. Yeah, then that means, okay, so could it be, so that means you can have different orientation with the same then twist. Is that, because it's ON plus. So it's not necessarily preserve orientation. You could have two orientations. It seems that you have two orientations, then you have a then twist. Then twist has to be okay. So what's your question? That's
my question is like, if you pick one orientation this way, and then pick the other embedding this way, so one is turning this way, one is turning this way. So these two give the same then twist or not?
So when you say that the turn is opposite orientation,
one horizontal, one vertical.
What do you mean? And this, and tip the map. You mean so if you look at S1, I mean, if n is 1, then either it's clockwise or anti-clockwise.
Okay, yeah.
So if you have S2, of course, the don't twist it's just relate to antipode map, rotate. Same, doesn't really matter. It's just like the Hamiltonian flow is uniquely determined. So yeah, you can have. I mean, that's it could be like you have one turn twist, and then other one just reverse the direction.
Okay.
So there's no maybe when you say the horizontal and vertical.
Can I pick the north and south to be these two instead of these two?
Okay, so that can be related by the
rotation.
Rotation.
Okay.
Yeah.
Okay.
And then according to that remark,
okay.
The in the pi 0. What do you mean by n less than 3 or not higher than n is?
So
not level. So
without this, we can prove that the then twist is the same if you got this property.
Okay.
Yeah. So yeah. If you have this case, then you don't need to care about this. It is automatically the same. Yeah, but for higher end you can't do, so you need to check this.
So for high, why is not?
He said he just don't know how to prove.
Then when you say often, okay,
yeah, he cannot use this way to prove. So yeah.
I see.
Yeah.
That is differential topology pi. Okay, then is.
Yeah. Okay. So yeah, for our purpose, we will use the then twist.
So this home topic class is in the pi 0 of symplectic morphism, right? Yeah. So it's symplectic morphism. It's I mean when this equivalent class of the then twist tau L.
Oh yeah.
So this is a symplectic morphism.
Yeah. This one is in the symplectic morphism. Yeah. This one is in the, yep. Of E. Yep. Correct. Yep. So yeah, but for our purpose, we will pick this such that you twist the puncture 180. Okay, and then next, why we always talk about this AN configuration sphere is because these then twists on this sphere will give us a braid group action. So remind ourselves what is AN configuration. So AN configuration is just what you should think of as the dinking from the dinking diagram. So they don't have intersection when they are far, and the intersection is 1 if they are adjacent. Okay, and then now lead to a very important result, which is lemma 5.1 from the Lagrangian two sphere can be symplectic. Symplectically noted paper that if you do then twist on the first Lagrangian do the L1 then twist on L2 is actually equals to the connect sum of L1 and L2. It's also Lagrangian isomorphic to the inverse of L2 then twist on L1. Okay, this is briefly taught by Brian last time, and the proof is analytic and topology. So if you are interested, you can go and look for the paper. So Lagrangian isotopy means there's a smooth family of Lagrangian. The isotopy is formed by a smooth family of Lagrangian subuniform. And from this lemma is quite.
Is there any condition for the intersection, like any condition on L1, L2?
Yeah, condition L1, L2
okay.
is
only
from
one intersection point.
Yes, coming from this AN configuration. Yeah, so you can replace it by I plus 1I, or yeah, something like that. Yeah, and then so one powerful stuff you can get from this lemma is the braid group relation. So the braid group relation is so from let's write it down. So from the definition of then twist, you can actually see that for F as automorphism, symplectic automorphism. So symplectic automorphism. Automorphism. You have this property here. So FL is equal to FTL F inverse, and then you can see that you have this two sorry, let me write it properly. So tau of L2 on L1, tau of TL1, so let me write the embedding notation. So inverse of L2. Okay, so this then twist I get from this lemma here. This lemma will imply this this equality, right? And then if you use this formula again, you expand the property out, what you get is actually the braid group relation after rearranging. So at first maybe you get this, and then second you will get this L1 T L2 T L1 T L2 T L1 T L2. Okay, so yeah, so since you have this braid group relation here, so you have a map going from the braid group into the pi 0 of symplectic automorphism of EW. Any question or not? And
maybe write on the braid group relation, just like
braid group relation. Okay, so braid group relation is I think the other relation maybe is easy, so in the Seidel paper they don't write down. So let me write down the braid group relation. So let me write somewhere else. Later I want to draw a diagram. So BR is, so this one is M plus 1, M plus 1. So sometimes we also call it AM. Okay, so this is because puncture you need to add one more number. So yeah, and then so braid group relation is like sigma I such that I is going from 1 to M, such that sigma I, sigma j, sigma j, sigma I for every I minus j greater than 2, and then sigma I plus 1, sigma I equal to sigma I plus 1, sigma I plus 1. Maybe this is obvious from the dentist, so Seidel didn't talk about this. Is this obvious? So if you have
because they are far away.
They are far away.
They are disjoint. Once disjointed to the neighborhood, they are also disjoint. The don't twist is only in the local, in the away from the sphere, in the neighborhood. The ball bundle is don't twist. Away is identity. So that is
okay.
The second one.
The second one is what Seidel show as the connecting.
So this is long. It's lemma 5.4.
Yeah. Hey, do I give the? I don't give the reference.
Is this Lagrangian sphere can be symplectic noted?
Oh, sorry. Okay, so in this, okay, actually he proved in this paper, but they state in this. Okay, so let me write it properly. So this one is stated in graded Lagrangian sum manifold.
Okay.
But this one is proof in the appendix.
I see.
Yep.
Okay, so the lemma is in the graded Lagrangian.
Yep. Proof in appendix. And the proof is, yeah. Yeah, so if you're interested, you can look at the appendix.
And it's easy to see the Braid relation here. The
Braid relation is using, I think can use this lemma and the definition of dentist to get the braid. So after you get this, and then you can use the formula and then.
Okay. That's
maybe
same. You have inverse tau.
Yeah. Maybe I switch.
Okay.
Yeah, if you don't switch, I think you also can get. That means you move L inverse here and then move L2 inverse here. Then you exactly use this. I switch a bit. So one is inverse, one without inverse.
Okay.
Yeah. This one is hard, but this one I think is just from what we get.
Mm-hmm.
Hmm.
The lemma actually that is don't twist is can be think as connection sum. In the one dimension is easy to see. You can just and in high dimension you maybe need
they also write down the coordinate and then
yes, you need explicit expression, the flow, this Hamiltonian flow. It's called normalized geodesic flow. So it's coming. It's.
Do you know something about Lagrangian handle?
No, I know.
Oh, okay. Because they use that.
Lagrangian handle.
Mm-hmm.
You mean the proof? Yeah.
When they define the connected sum, they use Lagrangian handle.
Okay, so connecting sum. Okay, so they need it probably means if you have intersection, then you cut it neighborhood, or you cut then try to connect it then. So originally you have a cross, like you have two Lagrangian two spheres intersection point, and then locally like a two disk meet, and then if you remove this, and then you have to glue them. I mean, not by arbitrary connection sum. You have to connection sum in order to get again a Lagrangian. So maybe just preserve the Lagrangian condition. Okay. So then they call Lagrangian handle. I think it's just a Euro handle, and then you keep Lagrangian condition. So
but they only define it on 4 manifold.
4 manifold?
Yeah.
I think in general, maybe. I mean,
they only do it on the model.
Sure.
Base.
I mean, if you connection sum, you cut in 2 dimension. Actually, if n is 1, doesn't matter. Any handle is a 2 handle. It's like a handle half dimension.
Oh, okay.
But if in high dimension, you replace. So if you have say S2, you have 2 S2 inside 4 dimension, and then we intersect, and then you choose a disk. So you remove a disk. So you remove 2 disk, which is you think 2 disk you treat as D2 cross S0, which is 2 points, right? Because you have remove 2 disk, then you replace by S1 cross D1. Okay, in the 2 dimension you have 2 handles and 1 handles, right? So you remove 2 disk, and then you treat disk as these 2 disk cross 2 points, and these 2 points you think the boundary of S0 is like a boundary of disk D1, 1 dimensional disk. And when you do connection sum, you replace by disk cross S0 replaced by S1 cross D1, replaced by cylinder. You do connection sum, right?
So you're saying this is this part and this part here?
No, I mean intersection. You only have 1 point. Here you are not drawing.
You mean like this?
Yeah, okay, that is. And then you at that point, you move to disk.
Oh, you mean
small disk, right?
neighborhood of the
intersection? In each, you have each disk. And then you have two S1 boundary.
Yep.
And you connect them by
tube.
By interval, by the cylinder. Which S1 cross D1.
Okay.
S1. And then now you can't choose. You have to choose this S1 cross D1 itself is Lagrangian.
Okay. Yep.
If you choose direction, and then it's not Lagrangian, then glue together is not tangent sum is not Lagrangian. So you just choose the position. So that means the tangent direction.
Okay.
Because S1 you have tangent direction, and D1 you also have tangent direction, and these two tangent direction has to be Lagrangian, which is right. So because you can always locally can bend a little bit and such that these two direction is not Lagrangian. In 4 dimension. Imagine the 4 dimension.
Okay.
You have Lagrangian basis. So you have we already have S1. So you remove. So you have two S1. And you connect them by a disk. And then you just ensure that this S1 direction and the D1 direction, and these two directions have to be Lagrangian subspace. At each point has to be Lagrangian subspace. So that's this cylinder.
Okay.
Or maybe this is called one handle, or this one handle itself is Lagrangian. So maybe by Lagrangian handles just like is a handle, but itself is Lagrangian. Nothing but just evident, like a self-evident terminology.
Okay.
In high dimension, it's the same thing. You have high dimension, you remove a ball, which is the boundary is a sphere. I mean, you have Sn, you point, and then remove a disk. The boundary is n-1 sphere. You have two n-1 sphere. Now you joined by a cylinder. As D1 cross, right? You do connect them. You have a tube connect them. And this tube, now you have n-1 direction, which is as each sphere you have n-1 direction. And this D1, this cylinder, this direction has to be Lagrangian. You have only one direction left. You cannot move. So kind of very rigid. I mean, because you have to make sure it's Lagrangian.
Okay.
So Lagrangian, like half dimension, is like in terms of sympact basis.
Yeah.
You have the first half, and second half you probably can choose almost complex structure by certain rotation. But you already have n-1 sphere there. If that dimension tangent space is fixed, then you have one extra freedom. That's a freedom you have to make sure that together, the Sn-1 cross interval itself is Lagrangian. So then you can do connect sum, it is Lagrangian. Just make sure that you stay in the Lagrangian category.
The direction you're talking about, is it vector field or something? Yeah.
No, I mean the tangent space. You want to, you have the, suppose in the 4 dimension, the Lagrangian sphere is S2 and 2S2. And 2S2 they meet at one point. And each point we remove a disk. So the boundary is S1. So you have two S1, which is which is like punctured by two disks removed. You have a sphere, and then you join it by a tube, which is S1 cross D1, cross interval. Then S1 direction, suppose Xn direction is fixed. Then the other direction has to be in Lagrangian. You cannot you have to form a Lagrangian subspace in each point in the tangent space. You have to Lagrangian subspace.
Okay.
So what I'm saying that you do Lagrangian connect sum, you stay in the Lagrangian submanifold category of submanifold. And then so this Braid relation. So maybe.
And then I think I want to draw one last big picture. So you have a disc, just now what I draw, with W is the puncture. So if you consider all these puncture, so you can change the coefficient, right? So and then the fiber of this thing is EW, and you can relate DW to just W, and then this whole thing is a fibration over the configuration space of the mod DW. Okay, so this. So you can think of when I do the braid group, I'm twisting the punchet. So if you're twisting the punchet, when you twist, you can think of it as let's say the series of twisting, you can think of it as a configuration space. So this is something like a configuration space. So if you take pi 1, so this thing is equal to pi 1 of configuration space of the, and then just now we also see that this is also the same as pi 1 of W.
So W, what is W? Maybe what is W? Forgot what is W.
Okay, what is W? So just
W,
now.
Okay, remove the
coefficient
levels.
of the
Perturbation, deformation.
Yeah.
Okay, so
yeah. So okay, so when you, let me draw the picture again. So you got this. So these punches are written in WI. So the set of WI I call W. And then when you move around, you get, let's say you move a bit here, then you get a different W. So you move back to the same W again after you do the dent twist. After you perform this dent twist, you move back to the same set of W. So that's why we call it a symplectic automorphism of EW. So this EW is the fiber over a whole disc. So let me draw it. So EW is everything here. Okay. And it's different from what we said just last week, the week before. So last time we talked about monodromy of a singularity, right? So this is only on a single fiber here. So it's only on a single fiber. We only talk about single fiber here. So, but here we're talking about a collection of fiber. How the collection of fiber change. You know what I mean? Yeah. So the braid group action on this Milnor fiber is actually it's on Milnor fibration, because they move the Milnor fiber inside instead of a single fiber in the Milnor fiber. Yeah.
I just hope sometimes DW is like confusing with D.
Actually you can think of them as the same D. Actually you can think of them as the same D. Maybe the shape is different, but you can think of them as the same D. So what you do is you send a puncture here to puncture here. Yeah.
Okay, so that's the fiber. What is E sub W, subscript W, EW?
EW is you fix one set of W and then look at the Milnor fiber.
Okay.
If E is, you consider all kinds of puncture and then you look at every Milnor fiber. EW, yeah.
Okay.
This is actually a small W, small W. It's not a big W. Big W is
dimension. Let's go dimension.
Which dimension? Huh?
E and EW.
E and EW, yeah. Huh? Yep.
EW is dimension decreased by 2, right? So suppose E is 2n plus 2. So it begins with 2n plus 2. And then EW is 2n, right?
EW is 2n. Why?
Yeah,
what did you mean EW is the fiber, the set of fibers over the whole disk? Did you say it was a pre-image of the whole disk, or?
Right. Pre-image of a fixed disk. Fixed disk.
It's 2n plus 2 dimensional.
Yeah, I think both of. Oh, wait. I think I get what Brian said. Let me check.
And that first map is not the fiber; it's just an inclusion map. EW is included in E.
Right. Let me write the.
This actually explains. I was looking back at Kovenov-Seidel section 3, as you said, where the paths C are defined, and this explains the boundary in the homology, I think, too.
Oh, okay.
Because back there in section 3, it says that the boundary of your path C can lie on the boundary of the disk, and the inverge image of the boundary of the disk in EW is in the boundary of E. So there is some boundary issues going on there in E.
Which line you are looking at? Which page?
Oh, Lemma 3.9.
Oh, Lemma 3.9. Okay.
In the proof of Lemma 3.9, it says what happens if one of the endpoints of C are contained in the boundary of the disk. And then a bit later on back in section 6, I think it says the boundary of the disk in pre-image in E in EW can be is in the boundary of EW.
Yeah. Oh, so, actually, yep, right.
Maybe that's why they have that relative homology there.
Oh, yeah, right. So Brian, actually, they consider one extra line. So this line is connecting the boundary with the first puncture. There's one extra Lagrangian they consider.
Two curves, both which meet. Okay. Such that.
So in the proof, Brian, there's a what if an endpoint of a curve lies in the boundary of the disk, and then later on they talk about the pre-image of the boundary of the disk to be in the boundary of VW. I guess that makes sense.
Okay, so the so D is a two-dimensional disk.
D is a two-dimensional disk. Yeah.
Yeah. So usually, I mean, if probably we're thinking that the endpoint is always in the interior. So then suppose there was a okay, maybe one of these has endpoint. Yeah, could have I mean, these points usually is in the interior, but you're drawing on the boundary.
Which one? This one? Yeah. There's one extra Lagrangian sphere.
Oh, I see. Okay. Yeah. So it's one on the boundary. That has boundary, sure. Okay, so if the LWC is a sphere for the draw, the four of them, and the first one is only a ball, which is the boundary. That boundary is coming from the boundary of the disk.
Oh, okay.
Okay, so this is about the Braid group action on this. Actually, this Braid group action actually on the Fukaya category, right?
Fukaya category.
Here you only look at the isotopic class.
Isotopic class,
Because you can think that you can probably identify all the Lagrangians up to isotropy. And then the don't twist, you can only check don't twist, which is Lagrangian isotropy. Yeah, you can eat
right.
Lagrangian isotropy.
Topology also can only check up to isotropy.
Isotropy, okay. And then don't twist generate a Braid group. Right, so that is, this question is this Braid group. So this sympatmorphism of the fiber, EW. Okay.
Where is my W?
Yeah.
Okay. So you fix one set of W and then you move.
Yes. So E, what is the dimension of E?
I think you are correct because EW already fixed W, so it become 2n.
It's 2n. That's because I had Lagrange sphere, n sphere. So
yeah, I already fixed one of the variable W. So
yes. So if I'm just a bit confused about this W have
which one?
This W1 we have WI. So what is the coefficient?
WI?
We have all these WIs. That's the coefficient of this perturbation.
Right. Yeah, right. Because last time we formed the disk using those W. So yeah, those W will form the zeros of the polynomial, and then we use it to be the puncture.
Okay. Maybe we just do stop today, and then do you have more to continue more on algebra, like this? What? Poseidon. Do you want to give another talk, or maybe you want you had enough?
Because now I'm trying to understand the floor homology stuff, but I trying to understand the graded one, but I don't understand the thing they use, the object they use, like Lagrangian, Grassmannian, and then how to get the Moore's law index. Not sure how to compute.
So which paper you're doing? That's the Koranov and Seidel?
You can look at the Koranov Seidel page 57.
Okay, 50.
I'm not sure how to really get those things out.
57? Sorry. Grading of Lagrangian. Grading of flow homology. So what is you like examples, or you want?
I want to do grading. Actual computation. Because there's a similar story for topology. Topology I know because topology is like covering space, lifting covering space, and then you pick a generator and then you go and compute the grading. But I'm not sure what happened in this case. Like this Moore's law class, and then yeah.
So in terms of Koranov and Seidel, so how much you covered, or how much we have covered so far?
How much we have covered?
So if maybe so you want to understand Hollow cohomology? You want to?
Yep. I want to know how to compute how to get the chain complex.
But in this case, in your case, the intersection is only 1 point. So
But after twisting?
After twisting, I see. So after twisting, we should be able to using are we using non-dex sequence? What theorem? I mean, which theorem in that paper you want to understand? Maybe the
which theorem?
The 58, the proposition 518. That you want to?
Yeah. Also can, yeah. They want, yeah. Sure.
Or just maybe.
Actually, I want to see how to get lemma 6.17.
6.7.
5.17 or 6.17?
6. Because I'm not sure about the setup, so I can't verify the lemma 1.67. 6.17, sorry.
Okay, so this is
because in my project I need to get the graded.
Okay, so then we discuss graded Lagrange submanifold.
Mm-hmm.
Is that what
yeah.
we needed? Do you want me to explain something next week?
I know what they are doing, but I don't know what the thing they use.
Each article is graded.
Graded Lagrangian submanifold is more.
Seidel?
Seidel. I'm not sure what the thing they use, like Lagrangian Grassmannian. I don't know like what is the actual thing.
So maybe I'll give one that.
They say they are isomorphic stuff, then you can pick one to use. I don't know pick which one. I don't know what to pick from.
So this is Seidel's paper. And let's just check.
So which part of Seidel's paper are we talking about?
Graded Lagrangian submanifolds.
Okay. Graded Lagrangian submanifold. Maybe I have that. Oh, great. Okay.
And which page were you worried about there?
The entire setup. I don't know what actual space I need to use and how to use.
How it's set up. Okay.
I know how they set up, but I don't know like the actual thing to use.
So in that paper, which section you want to?
Maybe the basic notion. I can't really find any good like introduction book to this theory.
You mean the graded sympact geometry?
Yeah, part 2A, 2B, 2, yeah, the whole section 2.
Yes.
I can't do like actual computation.
Okay, so maybe because this is like a.
I can't find a good books on this thing. Do you know any?
No, there's no good. There's no book now.
There's no book.
Like a because it's still the theory is developing. And
okay.
It's not like a calculus. Since Newton and Leibniz, they did it just 300 years ago. But maybe there's some book. Some people maybe write a book, but
yeah.
Often, when you come doing research, often they spread everywhere. There's no different people develop for different things. They haven't have an agreement.
Okay.
There's no textbook which is everybody will learn in the first year calculus, starting from that.
But then how Seidel learn then? Seidel learn from where then?
We have examples. Some of there is a work by Arnold. I think Arnold Giventa has a survey article on sympact geometry.
Okay.
And then Maslow is some Maslow index. I think in Arnold and I think Giventa is a student of Arnold. Okay. And Arnold and Maslow and all these Russian mathematicians.
If they write in different language, then I can't understand.
I mean, not in Russian. I mean, of course, a lot of it in Russian. So that's the Arnold often say that all these Western mathematicians, they do it because they don't read Russian. They already Russian already did everything. But sometimes it's true, but not always. Okay, so maybe the next week I will do this basic notion. So the graded is what do you mean by graded? And then otherwise we can't move. And then we have to, so basically, I think in terms of category, we know that we can choose these, even though these M spheres in this AM type, there lies a chain of the spheres, and then one like a necklace, one by one, and only one intersection points. And then we do Deng twist, you create many other. You have a whole braid group. Braid group, you have these generators. You have M generators. The group is discrete group is infinite many elements. And if this, then you have this Deng twist. You have generators coming from the Deng twist of each Lagrangian. But as a group, is a huge group, is a braid group. So you let this braid group act on the Sakai category. But then up to the symplectic isotopy, essentially, you only up to this braid group element. So now I thought that the exact sequence we did last time will help you to do the computation. But obviously, you may need some grading to get more refined flow.
Right.
I think the next step is largely we could look at what is the graded different impact geometry. Okay, so I'll explain what is the graded impact geometry and then what is used for the further calculation. And
so Seidel's graded Lagrangian manifold section 2, section 2b is titled graded symplectic geometry, and then it has subsections A and B. Is it 2b brackets B that got an n-fold Maslov covering? Is that the sort of thing you're worried about?
Yeah. Yes.
Okay.
Yes. I think for this covariance Seidel, they push it to n equal to infinity, so that is it? I think so.
Yeah.
Yeah.
Has n less than or equal to infinity. Brian, I noticed that Seidel was a student of Donaldson.
Yes.
Yeah, he is. Yeah, he is.
The Seidel now itself have own school, Seidel school, have many students.
Yeah, he was a student of Donaldson back in the mid-90s, I guess. Was that right?
Yes.
Yeah,
so we have several students, which is very good. Like the Mohammed Abadaili and then Nick Sheridan. Nick Sheridan is from Australia. And
Mohammed is student of Seidel or Donaldson?
Yes, Seidel.
Is Seidel? Oh, okay.
Yes. Okay, so maybe next week we do this graded stuff. And then